Hey everybody. Today we're talking about box plots. A box plot is a single variable graph based on a set's 5-number summary, like this one here. When you look at the box starts at the first quartile and ends at the third quartile, with the median represented by a line in the middle. So that box is the middle half of the data. The arms extend out to the full range of the data, so they'll all the way down to the median and all the way up to the maximum. The box plot on that last slide was built using this data, so you can pause the video and do that for practice if you want, getting this 5-number summary and making a box plot of your own. The video previous to this one in the Normal Knowledge College Statistics course is all about 5-number summaries. If you just dropped into this video through like a Google search or something, you might want to start with that one. I'll throw a link up top. Box plots can be drawn horizontally or vertically. It doesn't matter. They each represent the same information. The choice between horizontal and vertical is really just a human choice based on what's communicating the data more clearly and more conveniently in a given context. Box plots typically display outliers separately. So let's do an example to see how that works. Here's a bunch of data. We want to give the 5-number summary, test for outliers, and then construct a box plot. So here's the 5-number summary, 62, 64, 75, 79, and 105. To do the 1.5 times IQR test for outliers, we find the IQR, in this case 15, 79 minus 64, multiply it by 1.5, and then subtract that value, 22.5, from Q1 and add it to Q3. So in this case, we get 41.5 and 101.5. Any values outside of the range from 41.5 to 101.5 will be considered an outlier. Looking back at the data, we see that there's only one value, 105, that doesn't lie in that range. So that's the only outlier in this set. All right, let's make the box plot. As usual, the box itself goes from Q1 to Q3, with the median represented by a bar in the middle. Now, however, the arms only extend out to the minimum and maximum values that are not outliers. So on the left, it goes to 62. The minimum value in this set is not an outlier. On the right, the bar only goes out to 90, the maximum value that is not an outlier. And then the outlier itself, 105, is represented with a point that's separate from that arm. Box plots are particularly useful when comparing data across multiple groups, as in this example, where we're seeing the distributions of petal widths in 3 different species of irises. Sometimes this is called a side-by-side box plot, and this is one of the most fundamental sorts of displays when you have one categorical and one quantitative variable. Some benefits to box plots. They're simple and uncluttered, and they directly communicate measures of center, the median, and spread, the IQR. Additionally, outliers are immediately apparent, which is very useful in any number of contexts. A major downside, however, is that they only display summary information. That's the cost of having such a clear display. And so you don't get to see the individual sample sizes in different groups. You can't tell from looking at a box plot if a box is representing 5 observations or 5,000. So here, for instance, we have a plot showing 4 different kinds of animals, carnivores, herbivores, insectivores, and omnivores, along with the total number of sleep that those sorts of animals tend to get per night. And you can't see it, but in this set, there's only 5 insectivores and 32 herbivores. So the sample sizes are pretty different. For this reason, individual points are also often represented on top of the boxes in a box plot, like we're seeing here. So for instance, in that insectivore box, you can see the actual 5 observations, and in the herbivore box, you can see the actual 32. So now the reader can tell that the sample sizes in those different groups are very different, and in particular, we might not read too much in to the box for insectivores because the sample size is so small.